artillery batteries fired over 1.5 billion shells. 70% of all combat casualties resulted directly from these strikes. Why, a century later, does French soil still conceal millions of unexploded munitions? Because the saturation rate far exceeded fuse reliability. 100 years after the war, unexploded ordnance continues to kill. Hundreds of millions of live rounds remain hidden beneath the earth. The forensic scale of this bombardment requires basic math. 1.5 billion projectiles equate to roughly 1,000 bombs dropped on every single meter of the Western Front. Up to 30% failed to detonate. They became permanent physical evidence of the crisis. Rusted iron cylinders lie buried in the damp clay. Their copper driving bands are heavily corroded. Inside the casings, the chemical compounds remain highly volatile. A single shovel strike easily triggers a lethal blast. Human tissue could not withstand the kinetic transfer. Shock waves liquefied internal organs. Jagged steel fragments severed limbs without direct hits. The survivors documented the true capacity of industrial ballistics. Thousands of veterans returned home with entirely pulverized facial bones, forcing military hospitals to pioneer early reconstructive surgery and build painted metal masks to cover the missing flesh. Industrial ballistics dismantled more than human anatomy. The sheer scale of structural damage shocked the command staff in August 1914, who considered Belgian fortifications mathematically invincible. The strategic error materialized at Fort Lonson, Liège. The garrison locked down inside heavy bunkers. Pre-war engineers poured this concrete to absorb strikes from 210mm guns, the known global limit. But the attacking forces rolled out classified prototypes, 420mm siege howitzers. The physics of the battlefield shifted. A plunging projectile weighing nearly a ton transfers catastrophic kinetic energy upon terminal impact. It bypassed the structural limits completely. The concrete rated for standard artillery fractured like dry paper. One heavy shell pierced the roof vault. It found the primary ammunition magazine. 350 men died in a fraction of a second. The resulting internal detonation physically deleted the installation. Lonson was just one node. 12 interlocking fortresses formed the complete defensive ring. Strategic planners calculated this exact barrier would halt the invasion for an entire month. The models failed. The massive kinetic strikes systematically disassembled the architecture. The entire network collapsed in just 11 days. Those 11 days of rapid destruction permanently invalidated pre-war engineering manuals, forcing European armies to abandon concrete and dig deep into the mud until the armistice. Stationary defense ceased to exist, while siege howitzers ground fortress concrete to dust, and even bloodier mathematics unfolded in the open fields. August 22, 1914. 27,000 French soldiers died in 24 hours. That equals roughly 18 men eliminated every single minute, without a break. Pre-war doctrine prioritized the offensive spirit. Commanders deployed infantry in dense tactical formations, relying on sheer morale to break enemy lines. They collided with the cold mechanics of indirect fire. French assault columns advanced shoulder to shoulder across the exposed terrain. Kilometers away, German spotters occupied elevated ridges and calculated grid coordinates. The invisible artillery strike arrived seconds later. Shrapnel instantly dismantled the packed ranks. French artillery units rolled their 75mm cannons forward for direct fire. Gun crews stood completely exposed. Their targets remained unseen. German batteries operated safely from reverse slopes, launching continuous bombardments without taking a single counter-battery hit. The kinetic density of incoming steel made surface survival mathematically impossible. Infantrymen collapsed to the ground. Sapper shovels bit feverishly into the hard, dry earth. Metal scraped loudly against rock. Soldiers dug shallow survival pits just to outlast the active barrages. Both armies desperately attempted to outflank these fresh defensive positions. Every lateral maneuver encountered a newly fortified perimeter. The tactical flanking race finally hit the ocean. Those temporary pits evolved into complex subterranean infrastructure. The resulting continuous trench line stretched exactly 450 miles. Tracing the chemical evolution of gunpowder explains how artillery achieved this relentless density of fire by 1914. What became the chemical foundation for this meat grinder? The formula originated with Chinese alchemists. They mixed saltpeter, sulfur, and carbon. The compound triggered rapid gas expansion. The earliest weaponized delivery systems appeared around the year 1. Infantry deployed fire lances. These were primitive bamboo tubes lashed directly to spears. The acrid smell of burning sulfur and charcoal choked the operators upon ignition. Flames and shrapnel ejected forward. The effective range stopped at exactly 3 meters. The expanding gas required harder containment. Metal barrels replaced bamboo. Cast iron cannons entered the battlefield. By the medieval era, scale increased drastically. Heavy siege bombards weighed over 20 tons. They propelled massive solid stone spheres to shatter fortress walls. But the chemical kinetic energy constantly outpaced the metallurgy. The raw explosive force remained permanently bottlenecked by imperfect smoothbore barrels. Gas pressure escaped around the round projectiles. Trajectories degraded. Accuracy failed at long distances. This physical limitation held armies back for centuries. The mechanical breakthrough finally arrived in the 1850s. Engineers cut spiral grooves directly into the steel. European militaries installed rifled barrels and locked-in breech-loading mechanisms. But the absolute breakthrough happened inside classified French workshops. Engineering transformed slow field guns into machines of mass slaughter. The French 75mm gun introduced a revolutionary hydro-pneumatic recoil system. The cycle was strictly mechanical. The crew fired. The steel barrel snapped backward on track rollers. The heavy gun carriage remained completely static. A fluid-filled hydraulic cylinder absorbed the massive kinetic strike. This energy transfer equaled stopping a car traveling at 160 kilometers per hour in under 1 meter. Then the system reset. Compressed air violently forced the barrel forward. A sharp hiss of vented pressure cut through the noise. The breech locked back into battery. The French government classified this hydraulic brake as an absolute state secret. To protect the design, the War Ministry scattered component manufacturing across the entire nation. One provincial factory machined the steel cylinders. Another isolated facility cast the pressure valves. Only the final assembly teams at the Puteaux arsenal possessed the blueprints for the complete internal mechanism. Older artillery pieces violently jumped backward upon detonation. Crews physically muscled the heavy guns back into position, losing crucial time to manually re-aim the sights. The hydro-pneumatic system eliminated this delay entirely. The gunner kept his eyes locked on the optical sight. The loader slammed fresh shells into the open breech without pausing. Pre-war designs managed barely 2 shots in 60 seconds. The new mechanism shattered those limits. A standard crew easily maintained a rate of 15 shots. The maximum limit was 30 rounds per minute. The fire rate of French systems at 30 rounds per minute immediately spawned a logistical crisis. British artillerymen received a strict daily quota, 6 shells per gun. Crews stood idle. How many shells does trench warfare demand? Pre-war logistics calculated a standard issue of 1,000 to 1,500 rounds per barrel. Quartermasters expected this stockpile to sustain operations for 6 months. Reality dismantled that math. A single 75mm gun exhausted the entire 6-month reserve in 1 hour of intense combat. Pre-war ammunition depots emptied out. Supply chains broke. State economies initiated total industrial restructuring. By 1915, France scaled daily manufacturing from 20,000 up to 100,000 rounds. The military drafted male workers into the trenches. Conveyors at new facilities required immediate personnel. Women took over the assembly lines. They manufactured artillery fuses and packed raw explosives. The production quotas demanded rigid 12-hour shifts. Constant physical contact with TNT and toxic chemistry triggered acute physiological reactions. The hazardous compounds dyed their skin a permanent yellow. Britain expanded annual production from 500,000, 70 million shells. Women entered the chemical plants and began their grueling shifts. In 1916, the main problem of heavy batteries was not the calibers. It was the breaking of a copper wire a few millimeters thick. Signalmen dragged the communication lines across the battlefield. A standard spool of field cable weighed over 40 kilograms. Laying it by running through an artillery barrage was a physically impossible task. A single shrapnel burst hit the mud. The copper snapped. The receiver went silent. The heavy battery instantly went blind. How to correct fire if the forward units had gone beyond the horizon? Aviation became the only technical crutch. When the ground lines failed, the trenches relied on human runners. Couriers took hours to navigate the shell craters. Most bled out on the way. The critical link between the massive guns and the advancing assault waves vanished completely. Commanders launched tethered balloons to restore the site. Ground winches hoisted the observation baskets to an altitude of 3,000 feet. Heavy binoculars revealed enemy troop movements up to 11 miles away. The giant hydrogen envelope acted as a massive acoustic membrane. It hummed with a continuous, low-frequency vibration from the distant artillery volleys. Spotters calculated the impacts and transmitted real-time coordinates down a secure vertical telephone cable. These static gas bags were highly flammable targets. Enemy planes hunted them with incendiary bullets. But balloon spotters received one crucial piece of survival gear. They had parachutes. The fighter pilots of the time did not. The canvas canopy provided a rapid escape from the burning hydrogen. In 116 American jumps, not a single parachute failed to open. Yet aerial observation remained a fragile substitute. Smoke obscured the battlefields. Clouds grounded the planes. The ground wires stayed broken. 0 hour arrived. The officers blew their whistles. The infantry stepped out of the trenches under the blind fire of their own batteries. Observers in balloons at 3,000 feet strained to spot target grids. But the artillery shells screaming overhead proved physically useless for trench warfare. Expectation: a high explosive detonation shattering the earth. Reality: a hollow flying pipe firing lead like a massive shotgun. Lieutenant General Henry Shrapnel engineered the core design back in the late 18th century. The mechanics were simple: a hollow steel cylinder, a timed bursting charge, and a payload of 200 to 500 lead or steel balls. A mechanical fuse ignited the powder mid-air. The shell casing did not shatter into fragments. Instead, it popped open and ejected the metal spheres forward. The kinetic energy of these lead bullets depended entirely on the horizontal velocity of the shell itself. Against infantry standing in an open field, this forward momentum shredded everything in its path. But a dug-in trench required a vertical trajectory. As the shell dropped in a steep arc, horizontal velocity bled out. The kinetic energy dropped to zero. The lead balls simply spilled downward through gravity. Battery commanders could lock onto exact map coordinates. The guns could deliver the shells perfectly on target. But the geometry of the battlefield neutralized the weapon. Against fortified underground shelters, a direct shrapnel hit yielded zero structural damage. Even when gunners switched to high explosives, a new disaster awaited the British infantry at the Battle of the Somme. The failure was not tactical. It was a manufacturing collapse. During the preliminary bombardment, 30% of all strikes failed to detonate. Why did a third of the fired metal turn into useless scrap? Factory haste and raw mechanisms. A heavy steel shell arced down from the sky. It punched deep into the trench mud. Inside the casing, the firing pin struck a defective primer. The chemical reaction stopped dead. Instead of a deafening blast, a dull, wet thud of metal hit the dirt. Deep underground, the German dugout survived without a scratch. The technology to destroy these shelters actually existed. Austrian super-heavy siege artillery utilized specialized concrete-piercing shells. Engineers equipped them with precise time-delay fuses. The warheads punched through reinforced fortress walls and detonated directly inside the underground rooms. But British mass production lacked this precision. In 1915, domestic factories expanded their output tenfold. The government hired thousands of unskilled workers to feed the artillery hunger. Conveyor belts sped up. Assembly quality plummeted. Workers rushed the delicate fuse construction, machined the metal poorly, and stored the finished batches improperly in damp conditions. The drive for sheer volume erased lethality. Factory speed inadvertently saved thousands of German soldiers waiting securely in their bunkers. The massive barrage pulverized the topsoil, but left the deeply buried defenders completely untouched. The scale of this industrial defect reshaped the continent permanently. Artillery batteries fired over 1.5 billion rounds during the conflict. Today, the European soil still hides over 300 million defective shells. With 30% of British high-explosive rounds failing to detonate, artillery engineers needed a workaround. They developed a pragmatic method to exterminate manpower without scratching the concrete. Early chlorine clouds relied entirely on wind direction, unpredictable, inefficient. The mechanical solution was ballistic delivery. In mid-1916, France loaded standard explosive casings with liquid chemicals. Germany immediately copied the design. Toxic payloads could now bypass thick bunker roofs entirely. The gas simply flowed down into the subterranean ventilation shafts. Germany categorized the new ammunition with painted symbols on the steel. Green cross for lung-destroying agents, white for tear gas, blue for mask breakers. Yellow cross delivered mustard gas. This was not a vapor. A heavy, oily mist of mustard gas settled at the bottom of deep craters. It waited there for infantrymen seeking cover from the shrapnel. 85% of all chemical fatalities in the war came from a single substance, phosgene. The compound proved 18 times more potent than chlorine. It required no blast radius to clear a fortified trench line. The invisible vapor bypassed effective fuses and impenetrable concrete altogether. It acted slowly. It left no immediate signs of exposure. Men sat in their underground bunkers and waited for lethal respiratory symptoms to appear over the next 48 hours. By 1918, British artillery could pinpoint multiple hidden enemy batteries simultaneously. It took just minutes after the first shot. While phosgene poisoned the infantry, British physicists in 1917 tackled a different crisis. How do you destroy a target you cannot see? British scientists answered with a network of acoustic stations. The mechanics relied on a strict physical law. The speed of sound is constant, roughly 343 meters per second. Physicists used this metric to calculate the exact distance to the blast. They deployed an arc of 6 or more microphones miles behind the front line. A heavy gun fired. The low-frequency boom rolled across the terrain. The acoustic wave hit each microphone at a slightly different millisecond. By comparing these micro-delays, officers triangulated the exact coordinates. Visual spotting became utterly useless when the enemy introduced flashless powders in 1917. But sound ignored visual camouflage. Academic science transformed into a lethal targeting system. The contrast in equipment dictated the survival rate. British networks processed acoustic data automatically through wired stations. Across the trenches, German soldiers stood in the mud trying to calculate blast distances with primitive stopwatches. The German army's stubborn reliance on manual timekeeping cemented their technical inferiority in counter-battery combat. At the Somme, British artillery fired for 7 straight days. The bombardment failed to break the deep concrete dugouts. To compensate for their acoustic weakness, the German command engineered a mathematical revolution. By March 1918, their artillery tactics changed completely. Operation Michael demonstrated the exact opposite. March 1918, German batteries unleashed 3,500,000 shells. They fired them all in just 5 hours. Commanders achieved this density by entirely eliminating registration fire. Previously, Gunners fired ranging shots to calibrate their aim. These preliminary impacts always warned the defending infantry. Now, pure calculation replaced the test rounds. An artillery officer opens his printed firing tables. He checks the latest meteorological data. He inputs the precise wind velocity and the current powder temperature. He calculates the internal friction wear of the steel barrel. No ranging shots, no visual adjustments. Crews lock the calculated angles. The sudden barrage strikes the exact grid coordinates instantly. A deafening, continuous roar hits the front line. 200 shells tear the air every single second. Integrating accurate weather data and powder temperature created the absolute foundation of modern ballistics, permanently canceling the need for physical zeroing. Synchronized equations broke the trench warfare deadlock, not heavier calibers. British scientists were developing the same techniques. How do you calculate a strike at a distance of 130 kilometers? You factor in the rotation of the Earth. The Paris gun represented pure engineering extremism. A barrel length of 37 meters, a weight of 138 tons. Flight time was so prolonged that artillerymen integrated the Coriolis effect into their firing solutions. 42 kilometers. The projectile breached the stratosphere. Air resistance vanished. No human-made object would fly higher until the ballistic missiles of the next war. It was a mathematical terror weapon designed to bypass the trench deadlock entirely. This obsession with sheer mass began in 1914. Krupp engineers created the 420mm siege howitzer, Big Bertha. The objective was simple: break the positional front with an unprecedented volume of metal. Deployment demanded perfect logistics. 200 men worked for 6 hours. They mounted giant steel mechanisms using specialized gantry cranes. Then came the firing sequence. An 800-kilogram shell left the barrel. The physical shockwave knocked the crews off their feet. Impact craters measured 6 meters deep. The Austro-Hungarian Skoda 305mm mortar supplemented this firepower. It penetrated 2 meters of reinforced concrete. But these super-heavy monsters remained static, inflexible. The tactical deadlock survived. The solution required shrinking the scale. Frontline troops needed weapons they could operate without railway access. The British Stokes mortar stripped artillery down to a steel tube and a base plate. Expert crews achieved a rate of 30 rounds per minute. While super-heavy guns demanded dedicated railway networks and massive logistical trains, this new design prioritized extreme mobility. Infantrymen dismantled the 108-pound mortars and carried them straight into the frontline trenches, while infantrymen carried mortars forward. Operating the heavy field batteries pushed gun crews to the absolute edge of human physiology. The routine started before dawn. The daily target list arrived. Officers assigned specific trench coordinates for total destruction. Batteries fired 800 to 1,000 rounds a day. Loaders hauled massive steel casings without a single pause. Commanders rotated shifts every 4 hours to prevent complete muscle failure. The physical toll was absolute. Offensives demanded even more. The preparation bombardment at the Somme lasted 7 days. Guns fired around the clock. The machines broke first. The relentless firing tempo pushed the weapon steel past its thermal limit. A barrel grew red-hot and deformed its internal rifling. A defective shell jammed and detonated directly inside the overheated chamber. The blast wiped out the gun and the entire operating crew. Enemy counter-battery fire systematically hunted these active positions. The air in the open gun pits turned toxic. The acrid smell of poison gas settled low in the dirt craters. Gunners choked. They could not wear protective masks while rapidly servicing the complex breaches. They inhaled the fumes and kept loading. Survival depended on location. Artillerymen lived surrounded by highly volatile propellants. Every gun pit stored dozens of ready shells right next to the firing platform. One accurate enemy hit on a forward position detonated the entire ammunition stockpile. To convert millions of fired shells into actual territorial gains, command required a new tactical algorithm. Artillerymen rigidly tied the attacking infantry to a strict mathematical schedule. They called it the creeping barrage. A solid curtain of high explosives dropped just ahead of the trenches. Then the bombardment shifted forward at a predetermined rate. The timing was locked at 50 meters per minute. Infantrymen checked their watches. They carried 30 kilograms of gear. They stepped forward into the smoke. The roar of the shifting firewall was continuous. Deafening blast waves drowned out all human screams. Soldiers had to march right behind the moving destruction. They tried to hold a strict distance of exactly 50 yards from their own exploding shells. 50 meters per minute equals a normal walking pace on a paved road. But the front line was a destroyed landscape of deep craters and liquid mud. Maintaining this exact tempo under enemy fire was physically impossible. The artillery plan forgave no delays. Portable radios did not exist. If a platoon stumbled in the mud, the barrage simply moved forward without them. The rigid curtain of steel outran the exhausted soldiers. This gap gave enemy defenders crucial time to leave their deep dugouts. German troops manned their surviving machine guns long before the attackers could cross the field. Generals engineered the creeping barrage as an absolute shield to protect advancing troops. Reality dictated a different logic, where maintaining the formation meant walking directly into your own shrapnel. French High Command calculated this bloody mathematics and established an official quota. The acceptable rate of infantry killed by friendly fire was 10%. This blind faith in the mathematics of continuous bombardment reached its absolute peak at Verdun. On February 21, 1916, 1,400 German guns opened fire. 1.4 million shells. Just 9 hours. The barrage vaporized the terrain. But sheer firepower carried a fatal physical flaw. At Passchendaele, the bombardments destroyed more than enemy bunkers. They destroyed the earth itself. British batteries fired 4.5 million shells in 10 days. Mathematically, this meant plowing every single square meter of the front line. This unprecedented density of impacts completely obliterated the fragile underground drainage systems of Flanders. Water had nowhere to go. Autumn rains turned the torn ground into a bottomless artificial swamp. Logistics collapsed instantly. Artillery could not advance to support the infantry. With every single shot, the violent force of the recoil drove the heavy guns deeper into the liquid mud. The offensive ground to a halt. Excess power became strictly counterproductive. The British advanced just a few miles across this wasteland. The physical cost was staggering. 250,000 British casualties. The earth simply dissolved. Mud swallowed men and tanks. The escape from that bloody swamp emerged in August 1918 at the Battle of Amiens. Artillery stopped plowing the landscape. It integrated into a unified information network. How do you suppress an enemy without multi-day artillery preparation? The British deployed sound ranging and aerial reconnaissance for precise mathematical strikes. 0 hour. A sudden, synchronous volley tears the morning silence. No preliminary bombardment, no warning, just calculated destruction. A reconnaissance plane patrols the sector. The observer spots a muzzle flash from a German gun. He transmits the coordinates via wireless telegraph. An Allied battery receives the data. Crews adjust the elevation dials. A kinetic strike obliterates the target. The shell destroys the German gun before British infantry even leaves the trenches. Data killed blind firing. Flash spotting and sound ranging dictated the battle. Specialized units deployed microphone arrays along the front line. The equipment captured acoustic shock waves from enemy guns. Officers applied complex trigonometry directly on the battlefield. They calculated exact firing coordinates in real time. Weaponized physics replaced raw tonnage. The branches operated as a single machine. Infantry advanced directly behind the creeping barrage. Tanks rolled forward. They crushed barbed wire. They flattened machine gun posts. Aircraft strafed communication trenches and bombed supply routes. Mass metal no longer dictated victory. Speed, exact calculations, and communication secured the breakthrough. In 1914, field batteries fought visually like in the Napoleonic era. By late 1918, armies finalized the technical structure of modern artillery.